All right, let's dive right in. So, for over a decade, Google has been on this huge quest, right? Trying to build a real working quantum computer. But now, get this, they're making a massive new bet. They're not just sticking to one plan, they're going after it with two totally different approaches at the same time. I mean, what if you had a computer that could solve problems we currently think are, well, unsolvable? We're talking about things like designing brand new medicines from the ground up, or creating materials with properties we can only dream of. That, right there, is the incredible promise of quantum computing. And make no mistake, this isn't some side project in a lab. We're talking about one of the biggest tech races of our generation. The outcome here could literally redefine what's possible for all of us. So to really get what's going on, we got to start with the absolute basic building block, and that's the qubit. Now, the regular bits in your phone or laptop, they're simple. They're either a 0 or a 1, on or off. But a qubit? A qubit is different. It can be a 0, a 1, or, and this is the crazy part, both at the same time. That's called superposition. The best way to think about it is like a spinning coin. While it's in the air, it's not heads and it's not tails. It's kind of both, right? It only picks a side when it lands. That ability to hold multiple possibilities at once is the secret sauce. It's what gives these machines their mind-bending power. And for a long time now, over a decade actually, Google has been one of the biggest pioneers in this space. They've been charging down one main path, and believe me, they've hit some huge milestones. That main path? It's called the superconducting approach. If this whole thing were a race, this technology would be the seasoned veteran. It's the one Google has poured its energy into for years, and it's the one that's already got some major wins under its belt. So what's so great about it? One word: speed. These superconducting qubits are just blazingly fast. They can perform millions of gate cycles, think of those as little calculation steps, and each one takes just a microsecond. That kind of speed is absolutely critical if you want to run the super deep, complex algorithms that quantum computers are famous for. But you knew there was a but, right? There's always a catch. They're incredibly fast, sure, but the big challenge has been scaling them up. Getting enough of them, we're talking tens of thousands, to all work together perfectly is a huge, huge hurdle. And this is where the story gets really interesting. Because Google just announced they're not just sticking to that one path anymore. They're officially pursuing a second, complementary one. So let's meet the new kid on the block: neutral atom computing. So what in the world is that? Well, it's actually kind of what it sounds like. Instead of building these tiny, complex superconducting circuits, this approach uses individual neutral atoms as the qubits. And how do they hold them still? With lasers. They use these super precise lasers to trap and manipulate the atoms. It's almost like having a set of microscopic tweezers made of pure light. Now here's the fascinating part. The strengths of this new approach are basically the mirror image of the old one. Where superconducting qubits struggle with numbers, neutral atoms excel. Researchers have already built arrays with 10,000 of these qubits. That's huge. Plus, they have this really flexible connectivity, where any qubit can talk to any other qubit. But here's the trade-off. They're slow, much slower. Their cycle times are in milliseconds, which is 1,000 times slower than the microseconds of the other guys. So this leads us to the big question, right? Why would you do this? Why invest all this time and money into two completely different, almost opposite technologies? Why not just put all your chips on the one you've been developing for a decade? Well, this is where you can see how smart this strategy really is. It's a two-pronged attack. Think of it like this. Superconducting qubits are easier to scale in the time dimension. Because they're so fast, they can run really, really deep and long calculations. On the other hand, neutral atoms are way easier to scale in the space dimension. You can just pack tons and tons of them together. So you have one approach that's great at time and another that's great at space. Let's break it down. Your superconducting qubits are super fast, but their big challenge is getting more of them. Your neutral atoms, you've got tons of them, but their challenge is running deeper, more complex circuits. See how they complement each other? It's like one team has a great offense and the other has a killer defense. By developing both, Google is tackling the whole problem from every angle. And you should know, this isn't some casual side hustle. This is a full-blown program. It's built on three main pillars. First, figuring out quantum error correction for these new systems. Second, using Google's massive supercomputers to model and design the hardware. And third, well, actually getting in the lab and building the thing at scale. You know, building something this revolutionary,
It's not just about the hardware and the physics. It's about the people. It's about creating an entire ecosystem to support the research, and that's actually a massive part of this story. To spearhead the experimental side of this, Google brought in a real heavy hitter, Dr. Adam Kaufman. He's one of the top experts in this field, and you can just feel the excitement in his own words when he talks about joining Google's team and expanding their work into this new platform.
And get this, Dr. Kaufman's team is going to be based in Boulder, Colorado. Now, that's not just a random choice. Boulder is basically the world's capital for this kind of atomic physics. It's a true quantum ecosystem all on its own.
And this is key. Google isn't trying to do this in a vacuum. They're diving right into that ecosystem. They're teaming up with major players there, like CU Boulder, JAILA, and NIST, and even their own portfolio company, Quera. The idea is to tap into the entire community's brainpower to push everything forward, faster. All right, so the billion-dollar question. When do we see the results? Well, Google is still super confident about their original horse in this race. They're saying we'll likely see commercially useful quantum computers based on their superconducting tech by the end of this decade. I mean, that's really not that far away. And that's really the bottom line here. This new neutral atom program, it's not a backup plan. It's an accelerator. The hope is that a breakthrough on one team, say an error correction, can be shared with the other team. They want the two paths to cross-pollinate, to help each other out, so that Google can reach its final goal even sooner.
So that leaves us with one final thought. Imagine it's here, a computer that can genuinely solve the unsolvable, born from this incredible two-pronged attack on the problem. If you could be the first person to use it, what world-changing question would you ask?